we can start with the second lecture. And now I'm going to go into some detail on camera projection matrices. And I have a Python script at the end that you guys can run. Now, I need to send that to you guys. I would, if you want to run it, I would recommend that you install Jupyter Notebook, and I can just send you the file because I'm having some issues with Colab. So maybe we can do that at the end, but does everybody have access to the internet? Nobody has access to it. So now we're going to talk about camera projection model and matrices. This is the outline of this afternoon. Talk about the perspective projection model, extrinsic and intrinsic camera parameters, camera calibration, and then one way to do camera calibration with just a single image. Now you may remember from high school physics that the way to form images is by focusing rays of light onto a plane or a surface. And the simplest way to do that was something that was discovered, thousands of years ago, or at least 1,000 years ago, which is the pinhole camera model. Now, what this entails is a small orifice in an opaque surface through which light can pass. Now, why do we need a small orifice here? Does anybody remember? What if we have just a big hole? Can we still get an image? Yes. But what would be the problem with that image? Distorted in what way? Overlap objects or overlapping rays of light. If you don't have this orifice, then rays from here will reach the image plane at many points, right? So the image of this flame will be diffuse over your whole image plane. So you can't get any detail. On the other hand, if you have this orifice, then now you're constraining the rays of light that come from any point, right? So if you have a ray of light coming from P, and if it has to hit this image plane, the only option is to go through the orifice. Now you've constrained points. If you have 2 points, that's a line. And so that the ray will intersect the image plane at how many points? 1 point. So 1 point on your object is corresponding to 1 point on the image plane, so you can get a detailed representation of your object. So a pinhole camera model allows you to project objects in the real world onto an image plane. Now, there are more sophisticated ways to do this where you can have lenses, and you can further concentrate larger areas into smaller points. But for the sake of today's discussion, we don't need to worry about that. This model is sufficient for us. Now let's look at some interesting parts of this model. We have what is called the optical center. In this case, the optical center is the location of this pinhole. This is a point through which all the rays intersect. And we also have this z-axis, which is the optical axis. Now that is defined as the axis that is perpendicular to the image plane. And we have the image plane itself, which is the xy plane. And the x and y axis are the horizontal and vertical directions on that image plane. Now we could abstract away these coordinates and have this geometric representation where we have this real world object point capital P, and we have its projection P prime. We have the height of the object y, we have its projected height y prime. And if f is the distance between the optical center and the image plane, then we have this relationship from similar triangles that y prime is equal to f times y over z, right? Because you have z is the distance here, and you have y, and you have f, and you have y prime. It's a simple relationship. Now what is f? Focal length. So what is the focal length? It's the distance between the principal point and the image plane, right? So the focal length is the distance between the principal point and the image plane. And so just like we have this relationship for y, we have the same relationship for x. And that's the simple pinhole projection. So what does this tell us? For some world point x comma y comma z, what do we get? We get the 2D coordinates on our image plane. And so it tells us how real world points are projected onto our image plane. And we can do this for any point, and we can get the projection with this model. Now for convenience, we represent this model like this. On the left, this is how a pinhole model would actually work. Rays at the top will go to the bottom of the plane, and so it inverts your object. The image is in an inverted representation of the object. But for convenience sake, we represent the image plane on the other side, right? And then we erect it vertically, right side up. And everything is still valid, right? It's the same. This triangle is the same as that triangle, but it's just more convenient. So we'll use this representation from time to time. Okay. So now we can define another coordinate system that is of interest. And specifically, I have three here. Two are ones we saw already, but now I have a third. So we have world coordinates. So say I have a bridge, then there's going to be some coordinate system that is convenient for the bridge. So I can call that the world coordinate system. I can decide where I be. But also the camera has a principal axis and an image plane. So the camera has its own coordinate system. So camera is taking a picture, it has its own coordinate system. I call that the camera coordinate system. And then when the camera takes an image, there's a picture of that bridge here. The image also has its coordinate system. X and Y you can call it, or you can call it U and V. They're all commonly used. So I have these three coordinate systems. I take a photograph of something. What that process is doing is it's taking points in world coordinates and it's mapping them to image coordinates. But to do that, we have to go through the camera coordinates because we know the location of the camera. So if we can find the location of the world with respect to the camera, then we can do this whole mapping. Okay? So these are the coordinates we'll look at. So let's look at how to go from world to camera coordinates. So say we have some world coordinate system, and then we have our camera coordinate system. We want to transform the points in the world coordinate system and represent them in the camera. In the axis of the camera, or that bridge column. Now, the way to do this is simply to apply a rotation and a translation. So say I have x tilde as my world coordinates, okay, if I apply a suitable rotation and then translate it suitably, then I should be able to represent x tilde in the camera coordinate system as x tilde sub cam. We need to determine what this rotation and what this translation are. But what I'm trying to say here is that there exists some rotation and some translation, and we can apply that to this transformation. Now, here we have two operations that we need to do. We have a matrix multiplication followed by an addition. But what people have done is to make this more convenient and to have a single operation instead of having two, they rewrite the coordinates as something called homogeneous coordinates. So what this does is it allows you to represent the rotation and the translation as a single matrix multiplication rather than having a matrix multiplication followed by an addition. So what are homogeneous coordinates? We just add one dimension to the image coordinates and one dimension to the scene or world coordinates, and we populate that dimension with the number 1. Okay. So why does this help? Now I can apply the rotation matrix to xyz, and then my translation vector can be added to the 1, can be multiplied to the 1. Because multiplication happens, the addition just happens as part of the matrix multiplication, and so I simplify the representation. From the homogeneous coordinates, if you want to recover your absolute coordinates, then you simply divide by the value of your last dimension, right? So say my homogeneous coordinates after some transformation becomes x, y, w. Then I need to make sure the last dimension is 1, so I divide everything by w. And so it becomes x over w, y over w, and similarly here for the scene coordinates as well. So in homogeneous coordinates, all scalar multiples represent the same point. So if I have 2x, 2y, 2w, that's the same as x, y, w, which is not the case for non-homogeneous coordinates where you have x, y is not the same as 2x and 2y. Okay. So in non-homogeneous coordinates, this is my transformation. But commonly what is done in computer vision is to use homogeneous coordinates. And so if I rewrite this expression with the homogeneous coordinate, I'm removing the tilde sign because this is the standard way things are done. My transformed transformation matrix has the rotation matrix, the translation vector, a 0 vector, and a 1. Okay. Now, if you expand this out, you will find that both of these are the same. Okay. Maybe you guys can take a minute and do that. If you have a piece of paper and a pen, if you just expand this out and you see what that gives you, I can do it also. Just to get a feel for it. So here I have R T 0 1, and then let me make this flat so I can write. My x is x tilde and 1, right? What's the size of x tilde? 3 cross 1. And what is the size of this matrix? 4 cross 4. Okay. So when I expand this out, what do you get? You get R times r times x tilde plus t times 1 plus 0 times x tilde plus 1 times 1, right? So what is this? This is r times x tilde plus t plus 1. So it's the third and fourth? Yeah. So this is the 0 transpose. So the 0 is this 0, 0, 0, and so 0 transpose is going to be 0, 0, 0. Yeah. Oh, sorry. Yeah. That will be in the next row, correct? Yes. So that. 0 times x tilde will also be in the next row. Okay. So that will be my result. So what is Rx plus T? Rx tilde plus T is simply x cam and then we have 1 and transpose. Okay. So you see that this is the same as x cam. So that's why people use homogeneous coordinates. It's so you have your image coordinates x comma y, and then I can put it in a vector x, y. I'm adding a third dimension and just making that 1. Same thing for the scene coordinates, the world coordinates.
Why is it called homogeneous?
That's a good question. I am not certain as to why it's called homogeneous. Do you know? I'll get back to you on that. I don't want to say something that's not accurate. It's probably something to do with. I don't want to guess, but I can look it up and let you know. But I do know that it's used in computer vision extensively, and the reason it's used is because it allows you to have a single projection matrix instead of having 2 operations. Is that?
No, I understand. Homogeneous kind of. It's like polished thinking and translation is lost.
It's not lost. It's still here, right? What is the size of this T?
XY.
No. What's the size of X cam?
XY is
Yeah, 3 cross 1, right?
T will be XY.
3 cross 1. What's the size of this T?
Same.
Same. So nothing is lost. There's no information that's lost. It's the same expression, right? You're just doing some manipulation and making it a single matrix multiplication instead of a matrix multiplication and an addition. That's the only. It's just convenient to have one matrix. Because well, you'll see that a little bit as we progress, and also in tomorrow's class you'll see that, but it's just for convenience. Other questions? Okay. So this allows us to translate between the world coordinate system and the camera coordinate system. Now, to reach our image, we need to then translate the points from the camera coordinate system to image coordinates, right? So we want to go from the bridge, which is now in the camera coordinate systems, to the image coordinate system. So I have my homogeneous scene or world coordinate, which is x, y, z, 1, and I want to get these image coordinates x, comma, y. And the question is, what is this matrix that I can multiply with this to get this expression? So here we're dividing by the third coordinate, which is z, because farther points are going to appear smaller in the image, and we are scaling it by the focal length, because if the focal length is farther, then the object is going to look bigger in the image. And so the vector representation of this is in homogeneous coordinates would be like so, right? We have fx, fy, and z. And why is this okay? Because in homogeneous coordinates, all points are same up to a scale. And if we normalize this, we can divide by z throughout, and we get fx over z, fy over z, and 1. Right? So that's our image coordinate. And the matrix we need to arrive at that is simply ff1. Okay? We multiply this projection matrix with our world coordinate in camera coordinates, we get our image coordinate. Now this is for the simple case where you have a pinhole model. But with most cameras, you have more than just that. So I have these expressions. I have my camera projection matrix. I have my homogeneous coordinate of the vector of my 3D point. And then I have my image point up to scale. Now it's important to note again that all points are the same up to certain scale. I said that already. And we can write it with 3 lines to show that equality up to scale if you want to drop the scale factor lambda. Okay. So now we can put it all together. Right? We have the translation, we have the transformation from the world coordinate to the camera coordinate and the camera coordinate to the image coordinate. And this is what we get. Now, in the previous case, we saw that this is a 4 by 3, 3 by 4 matrix. Right? We can split this as a 3 by 3 matrix and a 3 by 4 matrix, which would be as follows. We have a 3 by 3 matrix, which is simply the FF and 1. And then we have this canonical projection matrix, which simply transforms this 3 by 3 matrix into a 3 by 4 matrix, just identity and 0. Okay. And then we have the 4 by 4 matrix that we saw earlier, which does the world to camera transformation. So now if I have a 3D point in homogeneous coordinates, I transform it into camera coordinates, I apply this canonical projection matrix, and then I can transform it into image coordinates. And the output that I get is a 2D point. Okay? So this matrix, which represents the transformation from the world to the camera coordinates, is called the extrinsic camera matrix, and parameters R and T are called the extrinsic camera parameters. And then we have the intrinsic camera parameters, which represent the transformation from the camera to pixel coordinates. And these include, in what we saw, just the focal length, but they also include other things like the principal point and the scaling factors, which we'll look at those two in just a minute. But now we can represent this projection matrix as the product of these matrices. Okay, so P times capital X is going to be equal to lambda times small x, and P is K times this extrinsic matrix represented as R slash T. Now, when you write it as R slash T, what is the size of this R slash T extrinsic matrix? It's the canonical matrix times the world to camera coordinate transformation matrix. So what is that? 3 cross 4. So it's simply R stacked next to T. Okay, so the 0 and 1 here are no longer present because of the change in dimension. Okay. So now we have this convenient extrinsic matrix and we have this intrinsic matrix. We multiply them, we get the projection matrix. Okay. Now, what are the other parameters in the intrinsic camera matrix that we need to deal with when we have models which are more than just a pinhole model? Now, we already discussed that the principal point is the point where the image axis, the optical axis, intersects the image plane. Now, in the normalized coordinate system, the origin of the image is at the principal point. But in the image coordinate system, the origin is usually in the corner. And that's just because of the way usually we represent images. So if you open an image in Python or you open in MATLAB, the origin is going to be in the corner. But when you have the ray passing through the camera center onto the plane, then the center of that is going to be at the principal point. So to do this translation, we have to transform from this coordinate system to this coordinate system. And how do we do that? Yeah, but in this specific case, what is the translation matrix? Yeah, that's it. Right? It's just half the coordinate of the edge of the corner of the image in x and y direction. Right? So x naught by 2 and y naught by 2. Or if the image width is x naught and the image height is y naught, then it will be x naught by 2, y naught by 2. If the center is x naught, then it's just x naught, y naught. So it's just half the width and half the height of the image. You just need to translate it by those coordinates. So if those coordinates are simply px and py, then we just need to add px and py, and we get this new image coordinate where the coordinate system starts from the corner. Okay? And so our modified matrix is going to look like this. And then we can apply, we can incorporate this px and py into our intrinsic projection matrix by adding them at these locations. And so that results in this transformation. Okay? So we can see that expression here. Now, we also need to take into account the units. So what are the units of focal length and the principal point coordinates px and py? Yeah. So the focal length is is the same as the world units, right? Whatever that is. But for measuring image coordinates, what do we want? Pixels. So these are different units. So we need to add some factor to change the units as well. And these are called scaling factors, and they map from world units to pixel units. And here is an example. So we have a camera sensor here, right? We have some pixel size in meters of each pixel. So we can compute the factor mx and my, which should be the number of pixels per meter in each of these directions from the sensor, because the sensor has fixed number of pixels where each of those are responding to the light that falls on it. And we can get this scaling factor in terms of m sub x and m sub y in pixels per meter. And we can multiply this with our our calibration matrix in metric units, and then we get our calibration matrix in pixel units. So putting it all together, this is our camera projection matrix, where we have our intrinsic matrix and we have our extrinsic matrix. The intrinsic parameters include the scaling factors, the focal length, and principal points. And so that's for an ideal lens, but there are other factors as well. So all of these zero terms, if you don't have an ideal model or ideal lens, then it's going to be non-zero, and those actually do contribute quite a bit. So those are things that you have to take into account, and if you want to be very accurate. So you have things like the skew, and we have the radial distortion, which is the most important in practice. And we have the extrinsic parameters, which are the rotation and the translation relative to the world coordinates. So here's an example of radial distortion where you can see that straight lines in the real world are no longer straight in the image, and you have to do an undistortion to make the line straight once again. Any questions about this before I move on? Okay. So again, what are the main parts of my projection matrix? What is K here? What is K? The intrinsic parameters. And then what is R/T called? Yeah. The R and T are the extrinsic parameters, and together that's the extrinsic camera matrix. What does the extrinsic camera matrix do? Real world to? No. Camera coordinates, right? The extrinsic matrix does what? World coordinates to camera coordinates. And then the intrinsic matrix does what? Camera coordinates to image. Okay? Makes sense? All right. So now we can look at calibration. So calibration is figuring out what the parameters of my projection. Okay. So here I have a generalized projection matrix, which is a 4x3 with unknown quantity. Right? Here I have my real world points, and then here I have my image points. So in the most general case, I want to figure out all of these 12 numbers. In specialized cases, I can figure out T, R, and K. So how do I set up a problem to where I can figure out what these numbers are? P11 to P34. How do I do that? Sure, in MATLAB there's a function, yes. But what is the information that I need in order to be able to figure out? So how many quantities are here that I need to figure out? Thank you. No, here. 12, right? So how many equations do I need to find 12 unknowns? At least 12. So how do I get 12 equations? What would I need? If, say that again? Point correspondences. What does that mean? Corresponding points between the world coordinates and the image coordinates. That's right. So say I know the world coordinates of some points of which I also know the image coordinates. Then I know x, y, and then I know capital X, capital Y, capital Z. And so that gives me some constraints that I can use to start to figure out what these numbers are. Right? So given n points with known 3D coordinates, x sub I, and known image coordinates, small x sub I, we can try to estimate the camera parameters. That's our objective. So this is an example. Say you know the location of this origin, then you know all of these points because you've put them at known distances from that origin. And then you can take a picture and you can see what pixel numbers all of these points are at in that image. So now you have all of these point correspondences, and you can set up a system of equations to try to solve for the values of p. So how many points do you need? Well, actually, before that, why calibrate? Calibration is useful because it allows us to assess the geometry, allows us to do metrology, allows us to do alignment. So a lot of things follow from having these calibrated values. So that's why it's useful. Okay, so we have our equation between image and world coordinates. Now, because this is true, I can take the cross product between these two vectors, and that should be 0. Right? And if I expand that out, it's going to look like this, where here I'm simply taking the different rows of p and multiplying it with capital X sub I. Okay, so this is the same as this. This is small x sub I, and this is p times capital X sub I. So when I expand that out, right, if I convert this cross product into a matrix product, then it's going to look like this. From here, I get 3 equations, but how many linearly independent equations do I have here? The answer is 2. I only have 2 linearly independent equations. That's because one of these is the homogeneous coordinate. That's not giving me new information. So I only have 2 linearly independent equations. So even though I have 3 equations, the rank of this matrix is only 2. So I can only get 2 constraints from 1 point correspondence. So I can get 2 constraints, 2 linearly independent constraints from 1 correspondence. So what does that mean if I need to solve for 12 unknowns? How many points do I need? 6, right? So I need 6. So the projection matrix actually has 11 degrees of freedom. One of the numbers is not degree free, so it's going to be normalized by that. So there's only 11 things that I need to figure out, but I still need the 12 constraints at least to get a solution to this problem, if I'm looking at correspondences. I can also make other assumptions to simplify things, right? And if I know a reference, and if I know a scale, if I know the image plane is parallel, or if I know the direction of the axis, I can get more constraints, and I can reduce the number of points that I need. Now, one way to do this is to simply set up this problem and then solve as a least squares. But what is more commonly done is a nonlinear solution where you just minimize the error. We'll look at that more tomorrow. But for now, we can look at another simple way of doing a calibration with just a single image. Okay. Now here, I'm going to introduce the concept of vanishing points. If you have an image like so, where you can see that there are parallel lines, right? And this is an image we saw earlier. But these parallel lines are not parallel in the image. And that means that they're going to intersect at some point, right? So the point at which parallel lines in the real world intersect in the image plane are called vanishing points. So you have finite vanishing points or infinite vanishing points. If you have finite vanishing points, that would be the examples v1 and v2 here, right? Because you can write the location of V1 and V2. But if you have any axis of the image plane that's parallel to the camera axis, then where would that vanishing point be along that axis? The vanishing point is where it's going to be along the axis. The vanishing point is where parallel lines intersect. But if the parallel lines in the real world are also parallel in the image plane, then those lines will never intersect. So that would be V1, right? And that is called an infinite vanishing point. So that vanishing point occurs at infinity. So we have these three vanishing points. You can join vanishing points by a line, and that is called a line. One example of a vanishing line is the horizon that you would see. So here, if you see it, when I intersect these 2 points, it's kind of hard to tell, but it intersects at the horizon. You can sort of tell the sky is there, there's a building, and then you can see that. So another way to think of vanishing points is that they are image coordinates of points that are infinitely far away. And why can you say that? Because in the real world, these parallel lines will intersect only at infinity, or they won't intersect, right? And so if they're intersecting, then the point at which they intersect is, in the real world, infinitely far away.
So camera will be probably at that level. The way where camera is placed, probably it will be on the same plane as.
Not necessarily, but
Plane of the mesh. Like our eye line will be probably same.
so you can tell if the camera axis is above or below because the center, the optical axis intersects the image. So the center of the camera is the optical axis, and the optical axis intersects the image at what?
At the vanishing.
No, the optical axis intersects the image at the center of the image. So if you take exactly half and half, then that will be where the center of the camera is looking. And so if it's above that, that means the camera is looking down, and if the camera is looking up, and if the vanishing line is below that, that means the camera is looking down. And if the vanishing line intersects the center of the image, then the camera is looking straight.
I think when you place the camera,
Yes.
that it has to that optical line. What are the horizontal normal should intersect with the vanishing line. I'm thinking like that
That's not correct.
because
Because I can take an image right now of the ground. You can't see any vanishing lines if I hold it straight perpendicular to the ground. All infinite. So that's not true. But you can tell the position of the camera with respect to the horizon by looking at, or with respect to the vanishing line, by looking at whether or not the center is above or below.
the center of the image.
Of the image, yes. Right? But it's not true that the center of the image has to intersect the vanishing line. That's not the case. Other questions? So these vanishing lines and vanishing points, they give us an orthogonal frame of reference. And we can use that to constrain our problem. Okay? So how do we do that? So we saw that a vanishing point is an image projection of a point at infinity. Okay, so if you have x infinity, we have some point x naught, and then we have x infinity. Then we have this parallel line which intersects at infinity, and they all pass through this vanishing line, and we have the vanishing point. So x infinity is a point at infinity, and v is the projection of x infinity. So v is equal to p times x infinity, where p is the projection matrix we don't know. So we can say that assuming the point is infinitely far along the x-axis, just for argument's sake, say we're using the x-axis literally, then x infinity is going to be unit vector along x-axis times infinity, because it's infinitely far away. So we know the direction, and so we can just multiply that with infinity, and we get the location of x infinity. Now in homogeneous coordinates, this would look like this. Right? You have infinity, 0, 0, 1. But the way that this is represented in homogeneous coordinates is a modification of this. Instead of writing it as infinity 0, 0, 1, we preserve the most important information. What is the most important information for a point that's infinitely far away? The direction, right? So we want to preserve that direction. And so the way we write it is as so. We make the last coordinate in the homogeneous system as 0, okay, and the rest is a unit vector in the direction that point is pointing. So if it's the x-axis, then it's going to be 1, 0, 0, 0. Okay. So the only case for which homogeneous coordinates have 0 as the last dimension is for infinitely far points. And those points are only represented by the direction of that. Okay? So if you divide everything by 0, then the first one will become infinity, and the last one, 0 by 0, that's not defined, but this is how it's represented. Okay? Because we still have the direction information. So V is the vanishing point. Vanishing point is an image of an infinitely far point. So vanishing point is where parallel lines in the real world intersect on the image plane. Okay? But in the real world, those parallel lines will never intersect, or they intersect at infinity. So a vanishing point is an image of a point at infinity. So V is the image of x infinity. Does that make sense? X0 is just some point, and then along the x-axis in the real world coordinate system. And xt is the point again along that x-axis, and x infinity is just farther away along the same direction at infinity. Our ultimate goal is to figure out P. But yes, but we're not there yet. We'll get there in just a couple of slides. But you understand this? Yeah, that's all I'm trying to explain with this slide. Other questions? Okay. So now in canonical camera coordinates, just with a simple matrix, for any arbitrary direction, I have the unit vector in that direction followed by a 0 in the last coordinate, and then I have some projection matrix. Okay. So when I multiply this, I simply get the direction. So it still works. Okay. So it's a direction vector in the direction of that infinitely far point. Okay. So now I want to find P. Right. I can align my world coordinate system to be parallel to my vanishing lines, which are orthogonal. Okay, so I have V1, V2, V3, and I align my x, y, and z axis to be parallel to these axes. And now if I call each of these columns as P1, P2, P3, P4, what's the coordinate of x infinity? Capital X infinity, what's the coordinate of that? Well, that's the image coordinate. But what is the world coordinate of x infinity? 1, 0, 0, 0. right? So I have 1, 0, 0, 0. That's my real world coordinate of the infinitely far point. And when I multiply this whole thing with this, I'm just left with P1, which is this column vector. And similarly, I can do this for y and the z, and I get those P1, P2, P3. And this P times my real world coordinate is nothing but an image coordinate. And I know the image coordinate because I can extend those lines and see where it intersects on the image plane, right? So for V1 and V2, I can extend them and find that coordinate in my image coordinate system. And for V1, that's at infinity. So V1, V2, and V3 are the results of multiplying P with those coordinate directions. And then I can also do this. What is this coordinate? It's the origin, right? So I also have my origin. That's a projection of the world origin. And so this gives us 4 columns up to independent scale factors, right? But it still doesn't give us all the information we need to solve, but it gives us some constraints. We're basically getting these 4 points in the real world, and we have the corresponding points on the image. So if we align, like I said, the world coordinate system with the 3 vanishing directions in the scene, then and if I call them as E1 to E3, then I have these vanishing points, which is simply Vi is Kr times E sub I. And then I can take the K and the R to the other side. And because R is a rotation matrix, R inverse is R transpose. So I have R transpose K inverse V sub I. And I know that my vanishing directions are going to be orthogonal. So I can impose this constraint. And when I multiply those things, I get an R times R transpose. So what is R times R transpose? Yeah, identity matrix. So that disappears. And we're left with constraints on the calibration matrix. Okay, so we have this. How many constraints do we get? We get 3, 1 for each pair of vanishing points. How many unknown parameters does K have? It's a 3 by 3. So we have, in our simplified case, we have F, Px, and Py as the 3 unknowns. It's not up to scale, right? But those are the 3 unknowns. And so with just 2 finite vanishing points, we can solve for both the focal length and the principal point, because that gives us the constraints that we need. Now, traditionally, this is done using nonlinear optimization to solve for these, but we can also do it in a simple way. So here is a summary of the vanishing points. When we have 1 finite vanishing point and 2 infinite vanishing points, like in this case, then we can't recover the focal length. And the principal point is just the 3rd vanishing point. But in these 2 cases where we have at least 2 finite vanishing points, we can solve for the focal length and the principal points. Okay. So once you solve for that, if you have to determine the extrinsic camera matrix, then you also have to try to get the rotations. Now we use the orthogonality constraint to solve for K. But once we have K, then we can write this equation again that we saw. And if I split R into 3 columns, R1, R2, R3, then I have this expression and when I multiply it with just E1, then that's going to give me R1. So R sub I is simply capital R times E sub I. Now, since we know that each of these columns should have a norm of 1 because it's a rotation matrix, then we don't have to worry about the scale for the rotations. And so in summary, we can solve for intrinsic parameters using the orthogonal vanishing points, and then we can get the extrinsic rotation from the vanishing points once we know k. Now the advantage of doing a single image is that you don't need multiple images and you don't need many 2D, 3D correspondences. You can automate this, but it only applies to certain kinds of scenes. It's tricky to accurately localize these vanishing points, and you need at least 2 finite vanishing points. In most cases, even if you think that your image is aligned, there's a chance that it's not, in which case you will have some finite vanishing points always. Okay, so how can you use this these vanishing points and the calibration to do something useful? So say we want to measure height with some reference. Okay. Now we have a camera center, we have a ground plane, we have this object, and then we have its projection onto this image. So say we have some reference like this person, okay, and then we have these parallel lines which are intersecting, so you can see 2 vanishing points. And say I want to measure the height of this column. So how would you do that? With the help of? Yeah. So I want to find the height of the column. I know the height of the man. Yeah, but the problem is, what's the problem here? Why is it difficult to do that? Because as you go from here to here, you're moving further away from the camera. So the number of pixels that correspond to the man here, if the man was standing here, there would be more pixels here, right? So say I have the base coordinate B0 and B for the man and this column, and then I can draw a line that passes through both these points, and then I have a vanishing point where these points, the line that joins these 2 points intersects my vanishing line. Then I have the top of this man. To find the location that the projection would be at, if the man was standing here, then I need to extend a line from this vanishing point through the man's head to this column, right? Then this would be the man's height, and then now they're at the same position. Now I can do the simple scaling, and I can figure out what the height of the column is, right? So now I have this man's height here, and then using R, which is the top of the column, I can find out what capital R is, because capital H over capital R is going to be equal to R minus B times R minus B over T minus B, right? But the problem is that I don't know where this, I need to figure out where this V is, and then I need to project that line, and I need to figure out what this point T is, right? That's the extra work that I need to do. Okay, so how do I do that? This is our scene. Okay, I have top of the object, bottom of the object, top of the object in the image, bottom of the object in the image. And say I have some reference point. I need to find this H over R ratio, but to to do that, I can take advantage of some known invariants. An invariant is basically some quantity whose ratio doesn't change irrespective of how you sample. So I need to find an invariant that I can use to figure out this h over r, given that I know these vanishing points. And the invariant that we'll use is this one. So P3 minus P1 times P4 minus P2, P3 minus P2 times P4 minus P1. I'm not going to prove this, but you can just take this to be true. And that ratio is invariant irrespective of where you sample from the vanishing point. So if I were to have some vanishing point and then I sample at a different location, a different angle, then this expression is still the same. Okay, that's what the invariant means. So it's also invariant to the permutation of the points. And now we can use that invariant to help us. Now we need a fourth point to compute the cross ratio. In this case, what would that be? What's the additional point that we can use apart from these 3 points? We saw that in the example that I showed you. It's the vanishing point, right? We have the vanishing point there. We have the image of that. And we can use that to compute the cross ratio. So in the scene, what is the invariant? We have t minus b times infinity minus r. Right? If you look here, it's p3 minus p1 times p4 minus p2. So I have t minus b times infinity minus r, then r minus b times infinity minus t. And that is h by r. That's the invariant. Now I have this for the scene. I also have it for the image. For the image, I replace the infinities by v sub z's. And then I replace the capital T's and the r's and b's by the small ones. Okay. So this invariant is useful for me to compute this ratio h over r. So this is the image cross ratio. I have v. Now how do we compute the coordinates of v and t? We can use this information. Say we have some equation. We can write it as a matrix product with a homogeneous coordinate. So I have small x is xy1, and then I have my coordinates, my factors a, b, c as another vector L, and then I have the dot product which gives me the line. Now if you want to obtain the point of intersection, or if you want to find a line that intersects 2 points, how do we do that? You guys remember from coordinate geometry? You just we want, so if a point is on a line, then what do we know about this expression? LT times x sub 1 if x1 is on LT. Then x sub 1 will satisfy the equation LT. If a point is on the line, it satisfies the equation. So LT times x1 is 0, and LT times x2 is 0. So now that I have these two things, if I want to find L given x1 and x2, I can simply take the cross product between x1 and x2. That gives me the equation of the line. And similarly, if I want to find the intersection of 2 lines, I take the cross product of the lines and I get the point of intersection. So x is simply L1 cross L2. If L1 and L2 are parallel, then what happens to x? Cross product of parallel lines, 0, right? So if I need to find v, I need to find t, right? I need to find the location of t. That's what I need to do. So for that, I can try to find v. I can find vx and vy. How do I find vx and vy? How to find Vx and Vy? Yeah, I can do that manually just by extending the parallel lines and finding where they intersect. Okay, and then I measure that. So I get Vx and Vy. So if I join Vx and Vy, then I will get a vanishing line. And then how do I get V? What is V? It's the point where what? Yeah. Yeah, it's the point on the vanishing line where the line that passes through B and B naught intersects, right? So to get, if I have 2 points, B, B naught, how do I get the line that joins them? Cross product. And similarly, Vy, Vx, I can get the line that joins them with cross product. So V is simply B cross B naught cross Bx cross Vy. Okay, so that gives me V. And then T, here, how do I find T? T is, well, T is where this V T naught line intersects the BR line, right? If you draw a line from V to T naught, extend it to T, B, and see where it intersects the line that joins B and R, that gives you T, right? So what's the line that joins B and R? B cross R. The line that joins V and T naught, V cross T naught. So I take the cross product of those 2 lines, I get T. So once I have T, then it's, you know, I know the height of the person, I know this height, I know this pixel height, I can just take the ratio and I get the height of the pillar. Make sense? So we're using these vanishing points to help us get additional constraints. And if we know where these lines intersect, then we can project them back into the scene. And we see how they intersect our reference bodies. And so we see where those lines intersect the bodies that we want to measure. And then we can make measurements. Make sense? Okay. So I have a script that I wanted to send to you guys. I will still send it, but not now. I'll just show it to you now. And then you can experiment with it later. Okay. I was just downloading so let me show it to you. So how many of you have used Python before? Okay. How many of you have not? Okay. So let me just quickly walk you through the script, and then I'm going to run it. Let me use my Colab version. Sorry, so here I had a blank part. Let me use this version. Okay. So here we have some function just to get the input lines. So the user can choose points that they want to select the vanishing lines. And this just plots them. This gets top and bottom coordinates. This computes the vanishing point by intersecting the vanishing lines. And this gets the horizon line, which is the vanishing line that intersects the vanishing point. And this plots it. This gets the camera parameters by solving those equations which I showed you. Right? I just use the solve function and then it does it. Then I can get the rotation matrix by again using the equations that I showed you. K inverse dot xyz. And then here I have the estimate height function. You can see I'm computing the cross products here, top line, vertical line, and then T minus B times VP transpose minus R, all of that stuff that we saw. And then I was trying to download some images of the campus here. Let me go here, and I want to show you a couple examples. So I have this one, IIT BBS. I can show you the image. That's the image. So here, how many vanishing points does this have? Well, it has one at least, because you can see the road there. It's parallel. Assuming it's parallel, then that intersects somewhere, and it might have other finite ones, right? Because it's slightly rotated. So let's try to use this one. Okay. I'm going to have to make it smaller so I can run it. Then, okay, so now what I need to do is select the vanishing lines. Now, I don't have a mouse, so yeah, if I don't get it perfectly, then it's going to not give me a good result, which is a problem. But I think I can choose this, and I can choose as many as I want. Right? Maybe there's something here. Maybe I can choose a couple of points here. Okay, so those are all parallel, right? Because they're intersecting. And then I hit enter. Oh, I think I hit enter twice. Oh no. But you can see here we can look at those images later. So now let's try another direction. So let me choose the vertical ones. Maybe I can choose these columns. I think that was a little bit off. Okay, so I have a few vertical lines, and here you can see they're intersecting very far away, right? So it's squished. And then I also have horizontal this way, so I can choose some lines here. And here also you can see it's pretty far away. But they're not really intersecting. I don't think I selected them properly. But let's see what it says. So it's estimated my F and U and V. Those are the numbers. And then I can run this. And I'm going to assume that the height of the pole is either 6.5 meters or 7.5 meters. I don't know if that's correct, but that's what I'm assuming. So I have the pole, and then let me see. going to choose building. And then I'll choose this column. And then I'm going to choose this tree. So now let's zoom into this. You can see what's happening here. It has projected this pole onto the line of the tree, right? And then you get that ratio for what that tree needs to be. So how accurate that is depends on how well I chose the vanishing lines. And here I can see the same thing for the column, right? So the pole is shorter than the column based on those vanishing lines. There. And then finally I can see it as well for the building. So the pole is on top of the building, that's what it will look like in the scene. We can see what that results in. So it's saying if the height of the pole is 6.5 meters, then it's saying the height of the building is 54 meters, height of the column is 9 meters, height of the tree is 5 meters. Okay. I think the tree is a little bit shorter than 5 meters, but I don't know how tall the building is, but for the column I think that's 3 stories, so 9 meters seems okay. Building is? And then how much is it? Yeah, so 54 is a bit high, I think. Yeah. So it comes down to how good your selections are, right? But also I didn't, the other thing is, the mistake I made here is that the dome is not at the same plane as this point, because it's further behind. Yeah, it's in the middle, whereas this point is in front. So yeah, so maybe if I selected it somewhere here, that would have been a better estimate. But this is 3 stories, right? Here, this column, 1, 2, 3. So I think for that the 9, how much is it? 9 meters. That one I think is okay. Yeah, and then so that I don't know how tall the pole is actually. Maybe 6.5 is high for the pole. Is correct? Yeah. But anyways, that's a tutorial. You can play around with this script. I'll send it to you guys. And I think that's 3:30. Any questions about this? So the main objective was to get you guys familiar with the camera matrices and calibration, what that entails, and to show you some like a practical example. So hopefully those objectives were met. Tomorrow we will look at how to collect data from drones, or if you're collecting data manually, what are the things you should take into account. And then in the afternoon we'll have a drone demo. And then finally we'll have a photogrammetry session at the end. Now For the photogrammetry, there's this software called Reality Capture. It used to be paid, but now it's free for entities that make less than some number of dollars, which is, I think, most people. So if you want to download it and see if you can get it installed, if Professor Jothi adds me to the WhatsApp group, I'll put a link there. Is everybody on the WhatsApp group? Yeah. And then you can download it, but if you just search for Reality Capture by Epic Games, you can find it. So it works better if you have a NVIDIA GPU, but even if you don't, you can install it. And I'll show you a demo with that in the last session tomorrow. So with that, we can create a 3D reconstruction with multiple views, so that's more accurate and more useful. Yes, I will share the slides. I just need a way to communicate to you guys over emails, or is there like an email list? Yeah, can you send that to me? Yeah, but do you want me to share the slides on WhatsApp? Okay, I can do that. Usually it's z-axis positive towards the image. Well, into the scene. Z-axis positive into the scene. Yeah. I'm not sure. You'll have to look specifically at the the manufacturer, because they'll provide the camera calibration. Which display are you looking for? HoloLens? They should. I mean, it's quite popularly used. You can probably find papers where people have used it, right? Generally, it's positive into the scene. Right. Yeah, so there are some foundation models that allow you to predict depth from a single view. One example is Depth Anything by TikTok. So what that does is it gives you a metric depth value for each pixel in the scene. And if you have your camera matrices, right? Because if you have your camera calibration matrix, then you can convert real world points into image points, but every image point still represents a ray in the scene, right? All points on that ray are coincident on the same image point, right? So that means if you have image coordinates, even if you have your camera calibration matrix, you cannot obtain the real world coordinates because you don't know which point along that ray that real world coordinate is. So you can get the rays, you can get all of the rays, but you cannot get the points. To get the points, you need one more constraint, which is the depth. And that depth you can get from deep learning. Or if you have an RGBD camera, you can get the depth there as well. But if you don't have that, then you can use these foundation models that predict depth. Now the problem is that these foundation models are not super accurate yet, but they're getting better. So that is one way I see where it will be possible. And you combine it with some semantic segmentation for a specific defect, then you can quantify that. Does that make sense? Yes. You get the f, but you're making assumptions, and then you get the f and the principal point. Fx and Fy. Well, in this case, you're just assuming that they're the same. If you're doing the multiple images calibration with the whole, yeah, I mean you can do it, or if you have a single image also with the many real world coordinates like that box that I showed, you can do, yeah. So you can do all of those things. But I didn't show you that. There are other calibration methods which are very commonly used and are more accurate and reliable, where you take multiple images of a fixed pattern, and then you can use that to calibrate. The problem with those methods is that if you're going out in the real world, then you're not going to get you can get the intrinsic parameters, but you can't. It's still difficult to get the extrinsic parameters from a single image. Yeah, you can't do it. So in this case, you can still get some useful information, and it's sort of a pedagogical exercise. But there are other calibration methods to get the intrinsic matrix very accurately. For well, if you have a checkerboard pattern, that is good. But I think the better one is if you have a 3D object with known points, then that's more accurate. Other questions? All right. So I think we're done. Jothi, anything else?